Hello and welcome to another video. We're going to be talking about the Powerseries convergence-radius characterization theorem. Now, what is the claim? So first, let us have some Powerseries ranging through 0 to infinity of some coefficients an times x minus x0 to n, and let this be a Powerseries. And let capital R be some number, and it can be anything ranging from 0 to infinity, including both, and let it be the Powerseries convergence radius. Now then, the series, this Powerseries, come up here, and it converges absolutely on x0 minus r x0 plus r. In other words, on the open ball with the center x0 and the radius r, hence the name. And it diverges everywhere else. It's a very nice property. When it's finished though, moreover, we have a formula for computing the radius. Fancy that. Is the limit superior as n approaches infinity of the nth root of the absolute value of an. Now, if the limit as n approaches infinity of an over an plus 1 exists, then we have that the radius is also equal to this limit. Like so. So we have the limit of an over an plus 1, both in absolute value. Now, for the proof, we'll have to accept the following convention. So I'll put it up in here. So for the purposes of this proof alone, assume that 1 over 0 is infinity and 1 over infinity is 0, right? For the purposes of this proof alone. You could do without this convention, but then you would have to single out the edge cases, and it's much more streamlined like this. Now, the proof. Put capital R, the radius, what would be supposed to be the radius, we want to prove it, equal to 1 over the limit superior of the nth root of an. Then, for all x, such that x minus x0 is fixed, is smaller than the radius. In other words, we are inside this ball. It holds that the limit superior of the nth root of an times x minus x0. Now, mind you, we are using the root limit test, for convergence of the series. So if this turns out to be smaller than 0, smaller than 1, but greater than 0, then it converges. And if it is greater than 1, then it diverges. If it is equal to 1, we don't know. Right, so this is equal to, and we can take out the x minus x0 because both of them are fixed. The only moving part is n. So we take them out. Like so. So we are left with the limit superior, the nth root of an in absolute value. But we have seen this before, right? So this is this from the definition of r. So this is just 1 over the supposed radius. And thus, we know that this is equal to x minus x0 over the radius. But we know that x minus x0 is smaller than r. So this is surely smaller than 1. And as such, the sum converges absolutely. I won't be lazy, I'll write it out. The sum from the beginning, from the claim, converges absolutely on, and now on this, in this ball, right? That will be just proven. All right. Suppose not. So for all x, such that x minus x0 is larger than r. For them it holds, and we want to show that this diverges, because then we will know it converges only on this interval or only in this ball, and it could diverges everywhere outside. So that is the convergence radius, right? By definition. Well, for all x, such that this is larger than r, it holds that what? The limit superior as n approaches infinity of the nth root of, again, we are taking the root limit test, or root convergence test, x minus x0, like so, to n. This, again, we do the same trick as before. We get x minus x0 in absolute value times the limit superior of the nth root of an. But using the same logic, we arrive that this is actually equal to x minus x0 over r, and we know that x minus x0 is larger than r. Right? Thus, we have something larger than r over r, and thus this is bigger than 0, and thus it diverges. So thus it diverges, meaning the sum, or the series. Altogether then, r is the convergence radius of the power series. Right, on to the second part of the claim. So assume that that exists a equal to the limit as n approaches infinity of an over an plus 1. Okay. Alright, so we shall now take the limit comparison test of the power series. So we have now that the limit as n approaches infinity of the absolute value of an plus 1 times x minus x0. So again, we are taking the limit comparison test of this sum, where we have n plus 1 over an times x minus x0 to n. Now, the brackets cancel out, and we are only left with the absolute value of x minus x0 times the limit and then approaches infinity of an plus 1 over an, both in absolute value. But we recognize this. This is this, but just the reciprocal value thereof, right? So we know that this is equal to x minus x0 over a. Now, we have that for x minus x0 in absolute value times 1 over a, being smaller than 1, the power series converges. But trivially, this is equal to x minus x0 is smaller than a. And this is an if and only if condition by the limit test definition, essentially. The theorem tells us that it's an if and only if biconditional. And thus we have that a must be equal to r. Else it would contradict the limit test. The limit test, the limit comparison test. Similarly, for x minus x0 times 1 over a greater than 1, we have that x minus x0 greater than a diverges. Again, a is r. And this concludes the proof.